from NASA. I probably don't need to read his bio, but I will because he's from NASA, and that's so cool. And the 10-year-old inside of me is so excited. I better put although I'm not 10 anymore because I need glasses to read this. So Ed Van Cise has been involved with the International Space Station operations since the first piece was launched into orbit in 1998. Working his way up through various consoles in mission control, Ed was selected as a NASA flight director in 2009. With a call sign of Carbon Flight, which we heard about yesterday, Ed has been a leader in the space station flight control for over 6 years. So please join me in welcoming Ed to the stage.
Well, thank you all very much. I think I'm going to totally disrupt the plan because we all love that, right, when we change the schedule and try to figure out how to fix it. So I'm going to skip to the very last slide, and I want to show you guys, this is, to me, the most exciting part of this whole talk, so I thought I'd just skip there, and then before you all fall asleep after having had lunch, and then you can sleep through the rest of it. So why don't we go ahead and go there, and let you guys watch this. This is time-lapse photography from the space station. So that's what your planet looks like from low Earth orbit. And I don't know, I watched this a lot, and it still chokes me up. So just a couple of takeaways just from watching that, which is maybe somewhat separate from the topic of my talk, but it's still linked together. Our planet is an amazing place, and the imagery that you saw is all just raw imagery. There's no corrections made to it. It's just time-lapse movies made out of the photos that the astronauts take. So, and also the aurora that you see in most of those images are actually the aurora australis. We get a lot better viewing of the southern aurora than of the borealis up north. So there's lots of New Zealand, Australia, etc. In those images. Questions people tend to ask me about the movies. So first, a lot of times astronauts get asked if they can see the stars when they're on the space station, and the astronauts tend to answer that a better question is to ask if they can actually see space. So you saw from the movies, right, there's very little black at night when the sun is down. It's because there are so many stars out there. It's just an incredible place to work and to explore. But then looking down on the Earth, you could probably make out some of the land masses based on the lights. The Nile River was there a couple of times, for example. The flashes, there are lots of flashes across the views. That's lightning. And what's really, especially when I talk to kids, school groups, what's really interesting to explain to them is that when it rains, well, I guess it doesn't rain apparently in Perth, but in other places, when it rains and you have a thunderstorm, you'll see localized lightning and big storms and things like that, but you don't really realize how large the weather systems are and how connected they are. And you'll see a weather map, and so like in the United States, it'll go across the entire country. But when you see it from space and you watch a lightning strike and it just triggers lightning that just goes from horizon to horizon, then you start to realize how big weather is and how integrated our planet is as a real living system. It's just truly amazing to be at a vantage point where we can watch over that. So I thought you'd enjoy seeing a little bit of your planet from a unique perspective. So now I'll just totally not have a good transition into talking about how we manage my baby, my spaceport in low Earth orbit, and how we do it well. So you saw this picture yesterday. This is the mission control, the flight control room number 1, where we manage and operate the International Space Station. Let's see. So let's delve in a little bit more about what I mean when we talk about mission control and what really happens in there. And again, it's going to be analogous to the same way you guys operate your major systems and for your missions. So each of the consoles in there is responsible for various subsystems or aspects of the spacecraft. Some of them are actual systems like power and thermal and life support and things like that. And then you have other groups that are responsible for the crew's timeline, the health and welfare of the crew, where you plug things in on the space station. So we've got over 100, 150 laptops deployed at any given time. We've got multiple wired and wireless networks. You can't plug certain things into the power source when you have other certain things plugged in because the criticality levels and things like that. So we have to have people that manage all those things. Every console in there is like at the head of that particular group, but there are other people in the background that are also helping them to provide all the data that is coming in for that particular area. And of course, they don't just graduate from college and show up in Flight Control Room 1. There's a documented process that starts even with hiring and then all the way up through certification. And it can take anywhere from, for some consoles, they can come from college or walk in the door, and about 12 months later, they can be on console. That's your best case. Some other, like if you're doing a spacewalk officer, that's going to be 3 to 5 years to get certified. But they don't just work in mission control on console. We spend about 30% of our time in the control room, and the other times are spent planning and preparing for the next thing. So you've got the flight director is at the top of the pyramid, if you will. Got the ultimate authority and responsibility for the outcome of the mission. And then the flight control team that's actually in the flight control room. And then you have a lot of offline help as well, people that you can call if you need to, people that are doing that planning for the next part of the mission. And of course, the crew is part of our team as well. So if you're in the airline industry, you know cockpit resource management. That's how the pilot and co-pilot and the flying team manages the cockpit. We have the same sort of thing on board, but then we also have space flight resource management, which you've got a team on the ground, you've got a team on board, and then the integrated larger team, how all of those teams work together to make sure we understand what's going on and work to accomplish the mission. And of course, we don't have stockholders, but we have program management and program oversight, just like everybody else, that tells us what our priorities are, what the mission needs to look like. And so you have a flight director at that level also that is managing the overall mission. Let's see. So how do we do our flight operations? We use a methodology called plan, train, fly. And I don't know if you can even read all the words that are on there. Oh, you can. That's good. But you don't need to. Basically, I think it makes sense that we're going to get requirements from the program. We're going to figure out if we can do them, how to do them. Then we'll train ourselves and the crews on doing them, and then we'll go fly the mission. So at the basic level, that makes sense. What's a little bit unique are two things. First, in the train box, you can see an item in there called next worst failure planning. And we spend a vast majority of our time focused on the next worst failure. Yesterday we called it what ifs, but that actually sets us apart from quite a bunch of operations organizations, is the extent that we talk about how we'd handle a failure after a failure has already occurred. And then you also see that the whole thing is tied into that orange box, that lessons learned box. So we're constantly doing lessons learned activities when things go well, when things don't go well. I think it was Jessica yesterday talked about celebrating failures as well as celebrating successes, and when the plans don't pan out. So we certainly do that as well. We want to make sure we understand what caused things to go well and do that again. We also, of course, want to understand when things didn't go well and prevent it from happening in the future. And then, of course, this is all also a feedback loop. So we're constantly telling our customer, which is the program, how we're doing in accomplishing the mission, and maybe they should consider changing the mission sometimes. So what I'm going to explain to you a little bit is how Mission Control is a high-performing organization and also a high-reliability organization. And when you combine those two methodologies into a single organization, you actually can expound exponentially increase your success rate. There's a lot of words on these pages. I'm not going to read them to you, and you can skim them as well. But there's the high-performing organization has 5 characteristics. The first 3 being leadership, design, and people. So how do we do leadership? Of course, we have an unambiguous chain of command. So the flight director is the ultimate authority in the flight control room. Whatever flight says goes. That's the final answer. We can choose to make a decision in a vacuum, but that's not going to be successful in the long run. So of course, we also train all of our teams to be leaders as well. You talk to me for a while, you'll hear me say lead your leader a lot, and that's one of our cultural items that we embed into our teams really early on, is that we want them to be leaders such that they lead their leader. So I don't want to if the flight director is the smartest person in the room, then that's going to be trouble, because I want the flight control team to be the smartest person, and I can just integrate what's being told to me. We specifically design how our things are statist. We want to be lean, but we also want to be and we want to be working towards that strategic goal. So, which right now, like I said, is for space station, is to being successful in our payload research and bringing those results back to Earth. So everything that we do is documented. Processes, training flows, certification guides, overarching certification guides, even down to the final console level. But if you have all this documentation, you either get behind really quickly, which we heard about yesterday as well, so that's a trap you can fall into, or you have to have a nimble process that allows you to make changes as you go. Of course, the people are the most important part in what we do, and we're very specific on the people that we bring into the organization. You try to weed them out in the interview process, but then we also have flight controller boot camp, and we progressively work through more complicated training until they get to the final simulations, where the flight director office will come in and do a final evaluation and determine whether or not a person gets certified. In the days where we had space shuttle flying, we would have the luxury of keeping people around that even though they couldn't get certified, they were still useful for office work. We don't have that luxury anymore. So if they, and it's told to them right up front, if they don't get certified, they don't get to stay with the organization. So the other two characteristics are how you handle change management and how you handle your culture and engagement in that culture. And like I was already saying, with change management, you need to be on target and on task, and you don't want to be swayed with every new idea that comes along. But at the same time, you don't want to be so rigid that you can't adapt to paradigms when they shift from underneath you, or new opportunities come along. So it's a balancing act. And then we are, our culture is something that's been developing for over 55 years now, and it's almost like well, we've got a military background is how this all started, right, with the Air Force and bringing that culture in. And I use the term boot camp, and one of the things we do with the flight controllers is we teach them how we want them to think and how they should learn and what they should believe, just like you do in the military boot camp, right? So everybody's got the same mentality, everybody's got the same understanding of the way we do things, so that at the base level, it doesn't matter which individual is sitting at, say, the ethos console. If they're ethos certified, then I know at the bare minimum of their capabilities, and I can trust them based on where they're sitting. So we have a lot of documents out there that we hold near and dear to our hearts, and you can read them there. So that's the theory. So how do we put it into practice? Talked a little bit yesterday just about the HTV and how that Japanese cargo ship, and it saved us from losing a bunch of supplies last year. And the HTV came up and delivered cargo, and we're able to not worry about bringing the crew home. But we did have a separate issue with HTV number 3, and specifically when it went to depart the space station. And just to give you a little bit up front, what's supposed to happen is the robot arm is supposed, the astronauts pull the trigger on the hand controller. The robot arm opens its snares that it's using to hold on to the cargo ship. The vehicle is supposed to just drift away, and the crews are backing the arm away, and then it'll eventually safely depart. That's the theory. So of course I brought a movie to help explain what goes on. So I think it'll play, and I'll just kind of talk over it a little bit. So this is grappled to HTV number 3, and it's about a 20-ton spacecraft, and it's going the same speed as us, 17,500 miles an hour, 28,000 kph. So the astronauts have released the snares, and it jumps out of the snares. We're looking at the very front of the robot arm in the foreground, and but it pops off, and the astronauts are. It looks like the HTV is moving away quickly, but they're actually flying the arm backwards. So the HTV really isn't moving. But we're going to back it away 4.5 meters, and then the astronauts will send a command to the HTV to wake it up and tell it to start departing. So they've stopped moving the arm. So what's supposed to happen is the HTV is supposed to very slowly start moving down in the field of view.
Houston Station on 2, HTV retreat is commanded, and the PT timer has been started. Right now we have a PT of 53, 54, 55, 56.
Houston copies. Nice job.
So when he said they commanded retreat, so they woke it up. And it's now figuring out where it is relative to the space station, but it knows it's supposed to wait for 5 minutes to drift away from the space station before it actually starts firing any thrusters. So it's actually still drifting, and like I said, it's supposed to be drifting down and away from the robot arm. So it looks like it's going down. That's good, but it's kind of going in the wrong direction. So it's gotten, from this camera view, it looks like it's gotten a lot closer. But it's still going down. For the folks on the ground,
Station
are starting to
Houston,
look at
for
it
a status, we see an
getting a
opening
little
rate
bit
of
too
0.5
close.
down here. We'd like to know what you see up there and also distance from the arm.
Bye-bye.
So orbital mechanics is supposed to be pulling it away, and that's the...
Okay, the range rate on the nav is about 0.011, and the distance from the arm is like maybe 2 meters.
Copy.
Yeah, so now the data's not matching what the crew's seeing and what the ground is seeing, but looking out the window, they say it looks like it's about 2 meters away from the arm. And remember, they flew it back to be 4.5 meters away. HTV does not know where the arm is located. It knows where the space station is, but it doesn't know where the arm itself is located. And so the HTV has decided it's way too close and it's getting out of there. So there's a bird's eye view. This looks cool on like Star Wars or something, but you never want a spacecraft to move that fast in real life when you're that close together. So what happened was, so it's an abort. The sensors on the HTV detected that it was, it has two things it's watching: where am I now and where am I going to be? And the sensors detected that it was going to violate a cone of, it's like a keep out zone. And so when it determined it was going to violate that corridor, it kicked off the abort. And so the vehicle, 20-ton vehicle, went from 0 to 1.3 meters per second near instantaneously with the 4 big engines on the back. So that's a lot of propellant going straight at the space station to get it out of there. It's designed to do that. It's a safe trajectory, and the important thing is to keep it from colliding with the space station. So it all worked, but it's certainly not the outcome you want to see. So I was the HTV-4 flight director. So this HTV-3 was in August of 2012. HTV-4 was in September of 2013. And basically we had about it was in August of 13. But by the time we got done figuring out what happened on HTV-3, we had about 9 months to go figure out how to make sure that never ever happens again. And so that was the challenge that was given to me and my teams. Don't let that happen again. But first you had to figure out what happened and why did it happen. And oh, by the way, HTV-4 has already been manufactured. It's sitting on the floor at the launch site in Tanegashima. So you're not allowed to make any changes to the actual spacecraft. And by the way, you can't really change any of the hardware on the space station either. So the most that you have to work with is software on the space station, and then your operational techniques. So we had to figure out what happened first. So orbital mechanics works. Sir Isaac Newton would be proud to know. But unfortunately, the robot arm is on the side of HTV, and so gravity actually is, in orbital mechanics, is pulling HTV straight down. And so you had the shaft of the grapple fixture inside the robotic arm, and it was pulling down on the bottom. And so when we opened the snares up and the astronauts pulled the arm away, it caused the pin to snag on the bottom of the arm, which it has a little lip on it, and it pulled it just a little bit towards the space station. But once you have inertia going, it's not really going to stop. So that's what happened. So we had to figure out how to not let that happen again. And so we were a high-performance organization, which means that we've got a very short turnaround task. We don't have the luxury of just very methodically working through it at a very serial basis. We had to get the Canadians figuring out what's going on with the robot arm, get the Japanese to figure out what HTV did, why it did it. Was everything safe? How do we what can we do with HTV to not repeat it? And then get that all back to the ISS program to figure out if what we wanted to do to adjust things would be safe and acceptable. So similar to the toothbrush conversation yesterday, what did the teams come up with? Well, they were set free to go come up with ideas, do good work, and then bring it back to us to integrate a solution. So the problem was that we pulled the arm back right away as soon as we opened the snares, because we want the arm to be away as fast as possible. Well, the solution was to open the snares and don't move the arm. And then Sir Isaac Newton and his laws will pull HTV out and down and away. And then once the shaft is out of the grapple fixture of the arm, then we can pull the arm away. So everybody came up with all sorts of different ideas. You could change the software on HTV. You could, if you just moved the grapple fixture to the top, then you could do whatever you wanted because it's going to just be straight down. That would be super easy. You can change the abort profile, so even if it happened again, it wouldn't potentially do any harm to things like our solar arrays. But all of that is time and money and a whole lot of work that we weren't sure we needed to go do. So the simple solution was just wait. And so that's what we actually ended up doing. It took a while to convince everybody that just doing nothing was the best answer. We had to, of course, write it down in procedures and train it and simulate it and go through all the the corner cases of what could happen. And it turned out that it actually worked really well. And so that's still the solution today, is we just wait. So that's a high-performing organization. So what about the other half, high-reliability organization? So we're also one of those. So the 5 characteristics of high-reliability organization, first half of that deals with preventing things from happening, and the second part is, okay, something happened. How are we going to handle it? So I'm going to give you another case study, again involving myself, because apparently I bring bad luck to the space station program. So it's not supposed to snow in space. We have 2 primary thermal control loops on the space station that flow liquid ammonia, but then each of our solar array segments has its own ammonia thermal control system as well. So we've got a lot of ammonia and a lot of ammonia pumps, and it flows it through radiators and rejects all of our heat. We had been tracking a very, very, very small ammonia leak in one of our power channel cooling systems for a number of years, and it was small enough we could just accept it and live with it. Then all of a sudden it started to snow, and the rate of that leak that we'd been watching for a long time just dropped off the charts. It was that was obviously what was leaking, and seeing a bunch of ammonia flakes outside is a bad thing. So ISS program said, we want you to go outside and stop the leak before the system runs dry, which would have been about 2 days. And yesterday from our conversation, right, we talked about in a normal spacewalk environment, you got about 12 months to go plan one. If you had to do one in a contingency time frame, we did it in 6 days for yesterday's example, but for just generic environment, you need at least 9 days. And so the ISS program told us we need it done. From when I got the phone call to when we went out the door, it was 36 or 39 hours, something like that. So why did we need to do it? We wanted to see where the leak was coming from, which meant getting to the work site before before the leak stopped. And of course, this was on our P6 truss, which is our truss way on the outboard side, on the port side. And our robot arm doesn't reach that far. So we couldn't just stick the robot arm over it and see where it was coming from. We had to put people out there. And we also had a Soyuz return coming up in 5 days. And they need 2 or 3 days dedicated to getting ready for that event. So we needed to get the spacewalk done before half of our crew came home. Otherwise, we wouldn't be able to go out there for another 2 weeks. So they challenged us to go do it. So you didn't have 12 months, you didn't have 9 days, you had 36 hours. Should we have had an accident? And like I said yesterday, it is the most dangerous thing we do outside of powered flight. And there's actually 2 different schools of thought that says, yes, we should have had a failure and should have had an accident. And an accident in this case probably would mean loss of the crew. So the fact that we didn't, either we were really lucky or we did something that challenges these 2 particular theories. So the efficiency thoroughness trade-off, I think it's common sense. When you have processes defined that says it takes X amount of time to go do these things, like 12 months to do a spacewalk, the shorter you make that, the more likely you are to skip a step or not complete something, and so you open yourself up to more risk, and that risk could lead to failure or error. And of course, instead of 12 months, 36 hours. We were certainly rushed. And then drift into failure says that when you have a complex operation or complex systems going on, those processes are generally going to be stovepiped, and then you need to make sure you have a good way of handing off data between teams. And your teams are very likely making decisions that make sense for their particular system or their environment, and it may not make sense in the global context. So you might have an engineer that says, well, this box is only certified to do this particular thing, so we're going to put a limit, we're going to put these limits in place, which is fine and good for that box, but in the bigger picture of what we're trying to do, that makes the whole spacewalk not possible. And when you have stovepipes like that and you're handing things off across shifts because we're in this rushed format where everybody's working 24/7, then again, you have potential for creating risk, not managing your risk properly, and then having mistakes or errors, and worst case, again, losing the crew. So why didn't we? Why were we successful? Were we lucky, or were we doing something else? And my argument is that we were doing something else, and the key thing is that we were mindful. We were aware of the decisions that we were making. So we were paying very close attention to our circumstances, our processes, and our culture, and in monitoring those three things, we were actually hitting on all the 5 characteristics of a high reliability organization. So what were our circumstances? So EVAs, EVA again is short for spacewalk, 18, 19, and 20 were set us up as far as circumstances go. So EVAs 18 and 19, you already heard about them. Those were the 2 spacewalks I talked about yesterday. So this issue that I'm talking about now was in May of 2012, and the spacewalks that I talked about yesterday were in September of 2011. And I was the lead for both of those, and that's one of the reasons I got the phone call for this one in May, is because I had just worked a couple of contingency-related spacewalks. Mini controllers had worked together. Is all supposed to be, I didn't do a very good job on these charts. Sorry. But because we had done those 3 EVAs in September and then November of the previous year, a lot of the flight controllers had already worked together doing spacewalks. The EVA 20 was a planned spacewalk, but it was actually at the work site where we needed to send these crew members to solve this problem. So in the past 6 or 8 months, we had done contingency spacewalks, and we had been at this work site. So everybody that was involved was already smart on a lot of those logistics, and had been through that contingency planning. The astronauts that were on board the space station had worked together at this exact work site a few years prior to replace batteries on a space shuttle mission. So our circumstances were perfect because we didn't have to explain to them how to get there, how to translate down the truss or anything like that. We could call up and just say, hey, we have this problem at this location, and they knew how to work together to get there. And so that saved us a lot of time. We were also very limited on what we could do. So there are 3 things that could be leaking: the radiator, the plumbing, or the pump. You can't access the plumbing. You can't replace the radiator. So the only option is to replace the pump and hope that that fixes the problem. So we were very, very narrow in scope of what our mission was going to be. And like it says, we were very smart on the technical details because of previous experience. So the ETTO model says that we need diversity of mental models, and drift into failure says that you need somebody who's watching the big picture and to make sure you're integrating across your silos. And so we talk about matrix management, and how matrix management a lot of times can be considered bad because people are not talking to each other. But if you do have somebody that's at that big picture level, and you have a culture that's good at talking across those silos, that's when matrix management can actually be very helpful, because you get both a very down and in perspective, and then you get a very good cross the system perspective. And we needed both of those mental models to be in play at the same time that we were releasing them to go do good work on their own. So we needed the power specialists to really think deeply about how their system is affected by what's going on, but then also realize they need to go talk to the spacewalking teams and the thermal teams and make sure that, and the engineers, they were all integrating and talking about the same thing. Because what's good for a thermal team may not be good for the integrated big picture. And that allows them to do a lot of the integration work. They bring it to me and the program managers of here's what we want to do. And then all we have to do, and I say all, but is stay aware at the big picture level and make sure that it makes sense, and then ask those probing questions. You know, did you consider this? Why did you reject this? And we're able to stay above the fray, if you will, managing the entire process. As far as our culture goes, maybe one of the more important things is that you're allowed to be wrong. You're encouraged to be wrong. Speak your mind. The expert can be wrong and make mistakes, and the co-ops can have big saves. And so we want to have all of those things brought forward, especially when you're very short on time. You don't want to have somebody sitting in the back saying, well, what about this? No, I don't know. I've only been around a year. I'm not going to bring it up because, you know, Joe's been doing this for 50 years. Then I get maybe some laughs out of this one, but everybody is involved, right? Even the managers. And some, you know, the managers were great. They brought in donuts and snacks and allowed the teams to be focused on their work. And they didn't micromanage, which is, again, knowing where your expertise is and letting your experts do what they're trained to do and encouraging them. But then also running interference for them when you need to as well. Being the squeaky wheel is okay. Sometimes, you know, the co-op will say, I don't understand this, doesn't seem to make sense. Everybody has to stop and explain it to the co-op, why it makes sense, and everybody agrees, yes, that still makes sense, and let's go. That's not wasted time or wasted effort, because when people ask those basic questions, especially all the I'm new here questions, it really helps to make sure that the fundamental understandings are correct. And my priorities and conveying your priorities to your team is fundamentally important. So I made it clear from the very beginning, priority number one is not to fix the leak. Priority number one is to bring the crew back inside safely. That might mean not even sending them outside. So everything was based on that. So we were successful. We replaced the pump. The pump turned out to be the problem. It didn't leak, and then we did another spacewalk about a year later to go refill the ammonia that was lost. And so now we're in really good shape. It's supposed to take us 12 months. Minimum contingency, 9 days. We did it in 36 hours. That must mean that we can do an EVA, do a spacewalk in 36 hours generically now, right? I mean, we watch it in the movies, right? Somebody says, you know, in The Martian, right? They go hop in the suit, they go outside. Why can't we do that in real life? So there's going to be a tendency, especially in the customer's mind, right? The program manager says, you did it once, why can't you do it again? And that's where you need your operations organization to really be aware and mindful of what brought them to being able to do these things. So you have to go again, look at your circumstances, your processes, your culture, and start at the beginning. And do this, you know, everybody wants to get started, and let's just start doing the work. But you have to take a step back and say, are we still in that same position? And you know, everything aligned perfectly in our situation to be able to go out and do this. And I think generically, you know, we've had to answer the question, can we make this the new paradigm? And the answer is no. 9 days is still the right answer. So talked about HROs, high reliability organizations, talked about high performing organizations. They can and do exist independently. You can have a very safety conscious, high reliability organization. You can have a very high performing organization. They get stuff done, great stuff, amazing stuff. They get it done quickly. But you get compounded interest when you have one organization that's adept at doing both of those things. So what that means is creating an environment where you can lead your leader, and they have the authority to make decisions, but at the same time, the ultimate leader still has overall authority and responsibility. You never rely on what worked before, and then you go back to that lessons learned environment. So every time you do something, so one thing that we could have done is said, hey, we did this in 2 days, we were successful, great, good job everybody, let's go have a beer and let's go home. But we picked this thing apart because even at the macroscopic level, it was successful. There are things that we did that maybe we should have done a little bit differently, and then we take those as lessons and feed that into the system to make it even better for the future. And that's, you know, we live in this environment of continuous improvement. And that's it. That's how we do business. And I'll take questions if you have it. Or I can show the movie again. Yeah.
Ed, you showed a process that you use to test your hypotheses, I'll call it, even if it's the wrong word. and it was plan, test, fly,
Plan-
or
plan, train, fly.
train, fly.
Mhm.
Okay. And I'm assuming you heard at least a few times in this conference, the plan PDCA cycle, Plan, Do, Check, Act. How do those relate? Are you missing something, or are we missing something?
Plan, do, check, act. We're not missing something. I'd probably argue that it's the same thing, just using different words. This makes it look like we plan as a separate thing, and then decide that we're ready to move on, and then do training as a separate thing, and then go execute. And in reality, we're doing all those things kind of at the same time. But I don't think that really answers your question. So,
Where do you test? What I'm missing,
okay,
where do you test
right.
what your plan is to make sure that before you fly, because I'm
Mhm.
assuming that fly is putting it into actualization.
Right.
You want to make sure it's right.
Yep. So that falls in. For us, it's in train. So testing falls into that, and so what we do as far as testing goes. So first, we're the ops organization, right? So we're not going to be doing testing to verify functionality. That is done and delivered to us. So like the contractor has a whole separate testing function to verify that they're meeting requirements and delivering something that's supposedly doing what it's supposed to. What we do so ideally all we have to do is train on how to use what's been delivered. But that involves taking procedures and products that we've developed and then testing those. So we do a lot of integrated software testing, for example. So the procedure will be to how to transition our command and control computers. And so we want to train our operators on how to do that, and at the same time test that our models and our integrated systems work properly. At the same time, we're testing it against the actual flight software, so we might uncover, and we frequently do uncover things to where it might match the code requirements, but it doesn't actually do what we want it to do. And so then we send that back to the contractor. So a lot of that falls into the training box, but I'd argue it's really the same thing.
Thanks for your presentation. I just got a question about change. Like any other organization, I assume you guys go through organizational change. So how do you manage that? And you talked about the culture. So do you have any examples of a major change you went through, and how do you guys have a process to manage it?
Yeah, it's a very timely question. So let me answer the cultural piece first. So the cultural piece transcends what we're doing. So the culture is our very basic root. It's our belief system. It's our values. It's our just our general how we do business at a theoretical level. So like plan, train, fly. It doesn't matter what vehicle we're flying. It doesn't matter our destination or mission. We're still going to take the plan, train, fly approach. And that's just part of our culture. The fact that any action, we could be called upon at any time to, how's it worded? At any time, any action we take could have ultimate consequences is one of our foundations of flight operations. And that's a cultural element to remind us that the lives of the crew is always in our hands and we have to take care of them. So that doesn't change. And so that's what we instill in our folks before we load them with our current state of thinking on how we're going to go fly or test or any of these other things. So then how do we change? We weren't very good at change, and we were actually pretty resistive to it because the model that we used for Apollo was the same model that we used for Skylab. It pretty much killed the flight controllers because Apollo is a short mission. Skylab is a very long space station mission. But then we did Space Shuttle with that same model, and we started flying Space Station with that same model as well. And it just became non-tenable and started to wear people out. So then we realized we needed to change, but it was kind of kicking and screaming. Then Columbia happened, and Space Shuttle was retired. And the money associated with Space Shuttle went away. And now we needed a flight control organization that still held to the same tenets, but we were more nimble and adaptable, and we didn't have to have 8 people in the back rooms because we couldn't afford them anymore. So we needed to change. And so we learned the hard way on how to do change. And so the way we did it is first we benchmarked. We went out and learned how nuclear power plants do flight control and their version of it. We benchmarked with the Navy. We benchmarked with other industries, aircraft, because for the first time we realized that we maybe weren't the best of the best, that other industries actually do the same type of thing and we could actually learn from them. And then we broke it down to like a training needs analysis. What skills do these flight controllers have to have, and how can we optimize how we train them? What expertise and skill set do we have to have on console all the time, and which ones are just augmented? And so now we have operators on the nights and weekends, and they can safe the system, safe the crews, and then we bring in specialists during business hours that have the deeper level of training. So I don't know if I answered your question exactly on how we did it, other than to say that we're better at change now. And we're at the point, so I said yesterday you need to try not to have paradigm shift underneath you, but actually look ahead to where paradigms might be coming. And so now we're actually smart enough to, maybe naive, but smart enough to say, okay, change is coming. Commercial access to space is coming. The commercial crew capability is coming. Space station is probably about 10 to 15 years away from being deorbited. That's a lot of paradigm shifts, and so let's posture ourselves so that we can be ready. So now we're talking about it, and how are we going to posture ourselves to be ready for when that change comes, and maybe even lead the change. I don't know if I answered your question.
Ed, thank you very much. It's wonderful to see someone who's still got that childlike passion about their role, and particularly in the pressure you're probably under. I've got probably 2 questions. The first one would be, if you were looking or basically interviewing for your replacement, what would be those attributes and probably the knowledge and experience you'd be looking for? And then the second one was, what roster do you work? Because it must be pretty stressful.
What?
Roster work. I don't know what you call it. We call it roster. Hours you work, days. How many days off? How many days you work and days off?
Yeah, the last question's easier. So we don't have a set rotation, really. It's a self-sign-up type thing. You're just supposed to work a certain number of shifts a month. Like I said, we end up working about 30% of our time in the control room. So we work, it's a 24/7, 365 operation, and you've always got a flight director on console. We do 9-hour shifts with an hour overlap at the beginning and the end. So in an ideal world, when you do shift work, is you work, say, 3 or 4 weeks straight, especially if you're doing overnights. So we basically violate every good study that's ever been done on how to do shift work, because we typically, at most, I'll do 5 nights in a row. Sometimes, 3. People ask me how I'm still standing after jet lag, and I got here at 12:30 on Sunday, and I was having drinks at 5 o'clock at night. It's because I've totally wrecked my sleep cycle. So maybe that's an advantage. But in general, we rotate. The flight control team is the same way, so everybody's on a different schedule based on their group's needs. And one advantage to just the way we operate is I don't need Joe to be on console at a specific date or specific time for a specific event, because whoever's certified to sit at that console, I know that they are qualified. And so we rely on that quite a bit. And the same is true for the flight directors. You kind of never know as a flight controller who you're going to get for that day or for that shift, because we're variable also. But you know what your minimum expectations are. So next question is, what are the minimum expectations if I had to hire a replacement? And we actually just hired a new class of flight directors, just brought on 5 more. And they all bring with them expertise. One of them actually is a former astronaut. It's our first astronaut turned flight director. But you have to have, they don't train us in leadership. They don't train us in teamwork. They don't train us in integration. They hire flight directors that already have that. And so the training that we get after we get hired is the same. We go through the same training, about 1,000 hours of training that the astronauts get on the space station. So I know this much about every system on the space station, so that I have a basic knowledge. Because again, I have people that can make me smarter as needed, when the urine processor breaks and things like that. But right away, you have to be able to come in and just, we're like the Google of space station stuff. So you just have to be able to pull information in from everywhere and assimilate it and then kind of put it in buckets. And so you just need people that are skilled at that. You have to be good at communicating, good at building teams. So with the HTV example, you had Canadians, you had Japanese, you had engineers, you had program managers. I needed them all to be working together, which is a lot. It might sound hard, and it's even harder in reality. If you've worked with the Japanese culture before, it's very different than, say, the Canadian culture. So getting all those teams to play nicely together. We don't get any diplomacy training either. But every day I have a direct line to the Russian flight director, the European flight director, which could be any European Union nationality, and then the Alabama payload operations director, which again, that's a different country. So you have to understand all those cultures and how to make it all work. And then you have to have a good attitude about it. I smile, I love it, like you said. I still have a childhood fascination with it. And I'll talk about it for forever too, because it is a passion. And the average life expectancy for a flight director is about 7 years. I'm on year 6. I don't sense myself burning out yet, but it is a tremendous amount of work. It's wear and tear on the family too. So, but I'm not going anywhere, so don't worry. Yeah.
Thank you for this wonderful presentation. Just have a question regarding, I guess, from asset perspective and the decommissioning an asset. I can imagine that decommissioning the space station, it's quite a massive logistic exercise and high budgets, and it's not that far away, and I suspect the planning should start in a few years, perhaps. I don't know, but would you like to comment about that and the size of the exercise and what may involve? I suppose it's not just left there. It has to be. Anyway, that's my question.
That's a fantastic question. So decommissioning the space station. So unfortunately, yet fortunately, there's an international treaty that says that if you put any object into Earth orbit, you cannot launch it unless you have a disposal plan. Now, it's up to each country to decide to adhere to that or not, but the United States does, at least as far as I know. And so from that perspective, the space station is just another thing in Earth orbit that you need to have a disposal plan for before you can even fly it. I'll confess we broke the rules. We didn't have a disposal plan until one of the safety organizations brought that up in front of Congress that, hey, we're violating our own treaty, or the treaty that we signed. So a lot of work has gone into that. It's a 420,000 kilo mass object, the size of a soccer pitch in Earth orbit. So it will so we have done a lot of planning on it. It will take between 6 and 8 months. Once we start the process of deorbiting it, it'll take about 6 to 8 months to actually get it low enough to where the Earth's atmosphere will pick it up and bring it in. We are going to, so those Russian cargo ships, that they actually bring up a lot of our propellant, or all of our propellant actually. So we're going to fly between 2 or 3 of those, and just to feed propellant into the system, and then we'll do the deorbit burns as a slow process. When it comes home, I selfishly, I kind of want to be the guy that pushes the button, just because I was there when we launched it. I'm going to watch it come in, but hopefully I'm retired when it happens, because I don't want to, it's a love-hate relationship I have. But when it comes home, it'll be pretty spectacular, and of course it'll be targeted to not hit New Zealand this time, like we did with Skylab. But I think right now we're actually targeting the Indian Ocean. I don't know the details of why, but that's what I've heard. But anyway, it'll be specifically targeted, and we have a lot of rules with overflight of populated areas, doing any of that sort of thing. So if we don't drop something on you by accident. I got the red light, so sorry.
Okay, please thank Ed for his excellent talk.